Good morning, Wallace. I'm going to go over some of the longer problems from the week 3 review here. I think I'm just going to do problems 1 through 3 for now. Maybe I'll do 4 and 5 a little bit later for you to take a look at. Okay, so I know you kind of like to have the review problems done in this way so you can sort of pause the video and take a look and figure those sorts of things out. So I'm going to share my screen here and we'll get right into the problems from the study guide. Okay, so this is for week 3 study guide. So let's go ahead and get into it. I'll just pull the first picture in here at the first problem. We'll go ahead and take a look. All right, so we have this isotropic steel alloy. It's common alloy in structural applications. A annealed version of this alloy has an elastic modulus of 192 GPa, Poisson's ratio 0.92. A couple things we're asked to do here. We want to determine the full stiffness matrix for this material, then the full compliance matrix computationally. Okay, we'll have to do it computationally. And then we're told some information about the stress that's on this object. Some stress here is given. And then we want to determine the contracted strain vector for this particular point. All right, so a lot going on here, but okay, let's get into it. First off, we need to understand what a compliance matrix is. All right, as a compliance matrix is part of Hooke's law. It relates stress and strain. So in general, something like stress is equal to the stiffness multiplied by strain. So you need to know the stiffness matrix. Here's your stiffness matrix. And here is your strain matrix. And here's the stress. Technically, these are vectors. So in size, this is a 6x1. This guy here is a 6x6. And this guy here is a 6x1. Okay. So what we're asked is to populate this stiffness matrix for this isotropic material. Right? So if you go to the notes and you actually take a look at the stiffness matrix for an isotropic material, it has kind of an unusual form and it uses variables that we don't see all that often. So let's go ahead and take a look at what that actually looks like. I'm going to pull that in here. This is right from the notes. So this is the stiffness matrix for an isotropic material. And we have these sort of unusual variables. You see this lambda here and G. G, you probably know, that's the shear modulus. Lambda, you probably don't know. Lambda is called the first Lemay parameter. It's just a variable that gets used because it's very convenient for this form of the stiffness matrix. So it's called a Lemay parameter. It's probably the only time you see it is when you do like finite element analysis, you see these 6x6 stiffness matrices, okay? So if you wanted to find the Lemay parameter in terms of things that you're more familiar with, it's more easy to understand what it is if you use things like elastic modulus, which is E, Poisson's ratio, which is nu. So we can define the Lemay parameter in terms of the elastic modulus E, the Poisson's ratio nu, as E nu in the numerator, and then 1 plus nu times 1 minus 2 nu in the denominator. All right. In this particular problem, we're given the elastic modulus 192 GPa, Poisson's ratio 0.92. So you can actually plug both of those things into this equation down here, and you can actually calculate what the Lemay parameter is straight away. And if you do that, you'll come up with a Lemay parameter equal 103 GPa. Okay, so that's for this particular situation. Once you have the Lemay parameter, the rest of filling this out becomes quite easy. You also need the shear modulus G. For an isotropic material, the shear modulus can be calculated. You probably learned this in an elementary mechanics material as the elastic modulus over 2 times 1 plus nu. This is for all isotropic materials. Again, we're given elastic modulus and Poisson's ratio here, so you can calculate straight away what the shear modulus is, and it's in this case 74.4 GPa. All right. Once you have these two guys, you can punch them into this 6x6 and calculate the stiffness matrix C. I'm not going to write the whole thing out here. I assume that you can do this simple basic math to fill in this particular stiffness matrix and entries here. If you really need some help here, lambda plus 2g, which is one of the main entries in the diagonal here. You see it in the 1, 1, 2, 2, and 3, 3 positions. Lambda plus 2g is going to be 251.6 GPa. Okay, so that's all you really need to populate the stiffness matrix C. So that's more or less part A, right? So part A is all this stiffness matrix stuff. The next is B, the full 6x6 compliance matrix. All right, so it says do not do the compliance matrix by hand. That's because that would be a nightmare, all right? So, I mean, it's not impossible, but it could be done. The easier way is to just say, all right, the compliance matrix S is the inversion of the stiffness matrix C. So after you've figured out and populated this stiffness matrix C, go to MATLAB, go to Excel, whatever you want to do, and do this inversion here. Do this in Excel or MATLAB, right? Preferably MATLAB. MATLAB's considerably nicer here. Okay, so you'll have to do this in MATLAB. Okay, you can do that. I feel confident in your ability to do that. And maybe I can just pull in the answers here. I do have the answers for this, so here would be your isotropic stiffness matrix if you really want to check yourself. And the units here are going to be 1 on GPA for units. All right, so if you want to check yourself, there it is. Maybe I'll make it a little bit larger. There you go. So that's the 6x6 isotropic compliance matrix. All right, so we see some negative entries there. That's perfectly fine. But that's ultimately what it's going to look like. I mean, I guess I could put in the stiffness matrix here too for part A if you really want to check yourself. So for part A, that's the correct answer. So there you go. That's the stiffness matrix for part A. You invert that and you get this, which is the compliance matrix for part B. Last thing we're asked to do in this problem is to calculate the strain given a certain stress on the object. All right, so let's make sure that we can do that as well. So we're given a stress state, right? So if you look in the problem, it tells you, all right, there's a point in our XY coordinate system with this particular stress state, all right? So we have to build the calculation for strain based on this understanding of stress. So the stress here is going to be, just as it always is, the stiffness matrix C multiplied by the strain vector. Well, we're looking for strain, but okay. So let's just put in our stress vector here. Our stress vector, remember, is like sigma x, sigma y, sigma z, and then we have tau. I gotta make sure I get this right. Yz, xz, xy. X, y. All right, so that's your 6x6 stress vector. So we're given what this is in the problem. If you go back up and you read the problem statement, this is 50, 20, negative 15. And then for your shear stresses, we have 20, 40, 50. And this is in megapascals. All right, so this is given in the problem. We need to then take this and calculate what is the strain. And the strain, given this information, is the compliance matrix S times the stress vector. All right, so we have the compliance matrix S, that's up here. So again, you'll have to do this computationally. We have the stress vector. So we have both of these things. This is a 6x6, remember? This is a 6x1. This is going to result in a 6x1 for the strain. And if you do that, you'll get the following strain values, or you should. 253, 51, negative 184, 269, 570, 538, and 672. And the units here will be in units of microstrain. Okay, so that is the answer here for part C for this problem. Okay, so this is just understanding isotropic materials, their full 6x6 compliance matrices, and then how to get stresses and strains using information about stress or strain plus the stiffness or compliance matrix to get you from one to the other. Right? Okay, so that's number one. Let's go on now to number two. And again, I'll just pull the problem statement in here. There's some relationship to problem one for this particular problem, so we'll have to reference back to some things about problem one, but okay. In problem one, calculated the strain state at a point in a steel alley from a given stress state. Assume now there is a separate 1, 2, 3 coordinate system. All right, so in your head, you want to have some visualization about, all right, there exists some XYZ coordinate system we have in space where we know a point that's in that space has a certain stress condition in the X, Y, and Z dimensions. All right, fine. But now they're saying, all right, there's another 1, 2, 3 coordinate system that exists in this space that is relative to X, Y, Z. So here's like a 1, 2, 3 coordinate system that somehow shifted or rotated relative to X, Y, Z. And these angles here are the angles that relate the coordinate systems 1, 2, 3 to X, Y, Z. So these angles here, like theta x1, theta y1, theta z1, etc. These are the angles between the x-axis and the one-axis. For instance, for this particular subscript, it's the angle between the x-axis and the one-axis. In this case, that angle is 0 degrees. So if you really wanted to be accurate about this, you would draw the x-axis and the one-axis as coincident axes. So that's kind of interesting to see here. All right, so if we were to draw this coordinate system a little bit more accurately, you would have actually the x-axis and the one-axis coincident because they have an angle of 0 degrees between them. You could keep going with this and look at, all right, well, what's the angle between the x-axis and the 2-axis? Well, that's 90 degrees. All right, okay. So between the x-axis and the 2-axis is 90 degrees. Well, I mean, that could be here, that could be here, that could be here, that could be here. There's a lot of different angles that could be. So we don't quite have the full picture of that 2-axis yet, but okay. Same thing with x-axis and 3-axis. There's 90 degrees between them. You know, there could be a lot of different ways that this thing could look. But okay, so there exists some other coordinate system, I don't know, 1, 2, 3, whatever, where there's angles between these various axes, and they're given as such. All right, fine. So what we're asked to do, assuming the stress state from problem one is again applied, so we have the same stress state, which is this stress state here. So this is again going to be applied in problem two. We want to calculate stress and strain at this point in the new 1, 2, 3 coordinate system. So taking information that we have in the XYZ coordinate system and transforming it into a different coordinate system, the 1, 2, 3 coordinate system. All right, so when we transfer between coordinate systems, we have slightly different equations that use what's called a transformation matrix. So if we're looking for, let's say, strain in the 1, 2, 3 coordinate system, and we want to use strain that already exists in the XYZ coordinate system, well, we can do that with something called the transformation matrix. Here, we label that as T star. And this is times the strain that exists in the XYZ coordinate system. All right, this is going to be a 6 by 6, this is a 6 by 6, and this is a 6 by 6. So these transformation matrices are quite complicated, and they're a lot to calculate, right? So for instance, here's the transformation matrix, which is T star. I'll just bring it in here. This is directly from the notes. So it's quite large, and it has a lot of these like M's and N's and things in it. So I'll scale this back a little bit so you can see this a little bit more clearly. But okay, M1 squared, N1 squared, P1 squared, N1 P1, P1 M1, blah, 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 blah. There's all these M's and N's and P's. And what the M's and N's and P's are, use the angles between the various axes that we know. So again, I'll take a picture here and bring this in for the M's and N's and P's. And so M's and N's and P's are going to look like this. And so it uses cosine of, let's say, theta x1, cosine theta y1, so on and so on and so on. Okay, so you can take these angles that are given to us that tell us the relationship between the XYZ and 1, 2, 3 coordinate system, these angles here, plug them in here to figure out what M1, M2, M3, N1, N2, N3, P1, P2, P3 are, and then take those values, punch them in here to figure out the transformation matrix T star, and take T star, plug it in here alongside with the strain that exists. Oh, by the way, these aren't 6 by 6. This is 6 by 1, 6 by 1. And now we can figure out what is the strain in the new 1, 2, 3 coordinate system. So a lot of steps here, but completely doable. It would be very similar for the stress. We have, if we want the stress in the 1, 2, 3 coordinate system, well, that's equal to the transformation matrix T. It's a different matrix than T star, multiplied by stress in XYZ coordinate system. All right. So let's bring in the transformation matrix T, which is specifically for stress. That looks somewhat similar to the strain transformation, but it's got some factors of 2 that float around that are a little different. All right. So this is for stress, but use the same M1 and M1 NP values, go in here, and okay, you can populate this guy. So it's very computationally intense. You'd have to, write a script in MATLAB or something to do all this, but it can be done, right? You know stress in the XYZ coordinate system. Again, that's given all the way back up here. This is stress in the XYZ coordinate system. It's given in problem 1. You know strain in the XYZ coordinate system. That's here. Again, we calculated it in problem 1. And so strain, stress, T star, you would have to calculate from all this. T, you'd have to calculate from all this, but it is known. So generally, you would be able to find stress in 1, 2, 3 and strain in 1, 2, 3. If you want the answers, I will give them here to you if you want to check yourself. So let's start with stress. Stress in the 1, 2, 3 coordinate system is the following. Oh, excuse me. Oh, I gotta find it. Oh, I don't actually have it calculated here. Actually, I don't have it. Well, if you give me a second, I can calculate it. You might just want to pause or fast forward the video a little bit here. It's going to take me maybe 10, 20 seconds to pull up this solution. So okay, so stress in the 1, 2, 3 coordinate system is going to be the following. 50 MPa, 28.6, negative 23.6, negative 5.2, 9.6, and 63.3. So that is the stress in the 1, 2, 3 coordinate system, and then the strain in the 1, 2, 3 coordinate system after doing your transformation is as follows: 253, 109, negative 241, 83.5, 130, and 851. And this is microstrain. All right, so that's the answer to part A of this particular problem. We're not quite done. This needs to go away. Why is this still here? Okay. Part B, we want to show that the von Mises stress in both coordinate systems is equivalent. That's easy. All right. The equivalent stress can be calculated in the 2 different coordinate systems as sigma 11, sigma 22, sigma 33, 23, 13, 12. This is all stress vector in the 1, 2, 3 coordinate system. So this is just plugging in. So you have stress in the 1, 2, 3 coordinate system. It's here. This is sigma 11. This is sigma 22. This is sigma 33. You get the point. All right, so take those values and punch them into the equivalent stress calculation to figure out what the equivalent stress is in the 1, 2, 3 coordinate system. Similarly, for XYZ, you have sigma XX, sigma YY, sigma ZZ, so on and so forth. If you go back to problem number 1 and you look at the stresses that were given in the XYZ coordinate system, okay, well, this is sigma XX, this is sigma YY, this is sigma ZZ, and so on, all right? So if you take those values and you plug them into the equivalent stress calculation for the second coordinate system, then these two calculations should be equal. And if you do it all correctly, then in both coordinate systems, the von Mises stress should be equal to 129 MPa. Right. Last part of this problem asks us about failure criteria. So lastly, calculate factor of safety against failure using von Mises failure criteria if the yield stress of the material is 470 MPa. Okay, well, this is just a ratio of what's the yield stress to the equivalent stress. So safety factor is, if you remember, yield stress divided by von Mises equivalent stress. So this here is 470 MPa. This is given for steel. That's the yield stress of steel divided by the current equivalent stress, which you calculated in part B is 129. These two things together give you safety factor of 3.6. Okay, so that's part C. And that's problem number 2. Let's keep moving on. Let's do number 3, and then we will finish this video. Okay, let's pull it in here. Problem number 3, unknown orthotropic material. Okay, you have an unknown orthotropic material and want to populate the 6x6 compliance matrix. So this is about you have something sitting on your desk, you want to go to the lab, you want to analyze it and understand its response. All right. You also want to identify it has some symmetry. Okay, fine. So the point is you ran all these tests in the lab. You ran 6 different tests, and those 6 tests resulted in the following material properties that you could evaluate. So you did a tensile test and you pulled on this thing and you evaluated, okay, what's the elastic modulus and the Poisson's ratio that I got from this tension test? And here they all are. All right. So we want to populate the full 6x6 compliance matrix for orthotropic materials. Okay, that's going to take a little bit of time, but it's not impossible. All you'd have to do is understand how the compliance matrix gets populated if you know material properties. And that actually just comes from the equation sheet for the class. It's part of the notes as well. So if you want to do that, here is the full 6x6 compliance matrix for an orthotropic material given material properties. So here, this is for part A. You have, for instance, the 1-1 entry as 1 on E1. So, okay, E1 that we tested in the lab is 80 GPa. So, 1 on 80 GPa, that's your entry in the S11 portion. Negative nu 1,2 over E1. Okay, well, here's nu 1,2, here's E1. Just punch those in, calculate, okay, well, that's the S12 entry, and so on and so on and so on. Okay, so you can populate all these entries. It would take quite a bit of time. I would say, again, writing code is your best friend here. So write some MATLAB scripts, write some codes to calculate what is this compliance matrix, given all these material properties that we tested in the lab. All right. So you can do that. I don't want to take the time and calculate them all here. That doesn't really make a lot of sense. Instead, what I think I'm going to do is I'm just going to give you the values here. So give me 1 second to put them in here. Okay. So here would be the compliance matrix. If you go through all of this and calculate it, you should get something that looks like this. All right, and this is going to be in 1 on GPa. So that's just taking the time to plug all these values here for all these material properties that we have. It's just, coding and taking time. All right, so that's not difficult. The real meat of the problem comes in parts B through D. All right, here's part B. Your test resulted in 12 engineering properties. All right, so if we go back up here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 engineering properties, right? But according to our information from the handouts and the lectures and the notes, you should be able to reduce down to 9 independent constants if you know that the material is orthotropic. So we want to show using numbers that the modulus Poisson reciprocity holds. And what modulus Poisson's reciprocity is that nu ij over E I is equal to nu ji over ej. So more or less what that means is, let's say nu 1, 2 over E1 is nu 2, 1 over E2. That's one form of this. Nu 1, 3 over E1 is nu 3, 1 over E3. And lastly, nu 2, 3 over E2 is nu 3, 2 over E3. All of these things must hold if the material is isotropic or orthotropic. So what you want to do is you want to just calculate each of these things. Like, just go to your MATLAB and say, all right, let's calculate nu 1, 2 on E1. Is that equal to nu 2, 1 over E2? You're just checking these things, all right? Checking these things. Checking these things. And you can do that, right? If you do that, you could get something that looks a bit like this. And I'll just pull in my code here so you can see the results. But okay, approximately, if you do the calculations, nu 1, 2 on E1 is 0.00422. Is that close to nu 2, 1 over E2? Because I'm evaluating this particular equation over here, right? And if you look at this, like, yeah, these are relatively close. It's within a couple percentage. So yes, check, they match. Same thing with nu 1, 3 over E1 and nu 3, 1 over E3. Are these close? Yes, they match. Very close. Same thing with nu 2, 3 over E2, nu 3, 2 over E3. Are they close? Yes, they're close, and they match. So this is just understanding this modulus Poisson reciprocity, that it holds true in orthotropic materials, and how does that look? All right, let's go on to part C. Can it be classified further as transversely isotropic? And this is the question then, is how do we prove or disprove that it's transversely isotropic? Well, for a material to be transversely isotropic, it has to have a couple of conditions be met. So if you look in the lecture notes, you can sort of see what those conditions are for it to be transversely isotropic or not. So I'll pull those conditions in here. There's a couple of different ways that you can think about it. You can think about it in terms of material properties, like relating E1, E2, E3, nu 1, 2, G1, 2, all that sort of stuff. You could think about relating stiffness and compliance matrix entries like S11 to S22, S33, those sorts of things, or compliance matrix entries. So C11, C22, C33, all those sorts of things. So if you kind of go to the notes and you look at what the conditions are to be considered transversely isotropic, you could think of it in terms of C11, C12, etc. So if it's transversely isotropic, this must be true. Okay. We don't really have the stiffness matrix. We have the compliance matrix. So in terms of compliance, it's a little bit different. And this is going to be in your equation sheet. So if it's transversely isotropic, you must have the following be true. So this must be true. Or compliance matrix. All right, so we just need to check these conditions. Okay, so does S12 equal S13? Well, you can go back up to the compliance matrix and look. Does S12, which is here, equal S13? Oh, yeah, it looks like they're pretty close. Not exactly on, but I'd say they're pretty close. So yes, this is good. What about S 2, 2 equal S3, 3. That's this condition here. Okay, is that true? Okay, do 2, 2, and 3, 3 match? Okay, here's 2, 2, 0.1818. Here's 2, 3, 0.1886. Yeah, there's a little bit of variation, but they're pretty close. They're within, you know, a percentage or two. So I'd say, yeah, they're probably close enough. All right, let's keep checking. Is S55 equal to S66? Let's go up. Let's take a look. Is S55 equal to S66? Yeah, again, those are pretty close. Again, within like a percentage or so. So yeah, those are pretty close. Last thing you'd have to check is S44 equal to 2, S22 minus S23. That's something you'd have to check, but again, it checks out. All right, I'm not going to go through the math here, but it would work. So yeah, if all four of these conditions are met, then yes, it is transversely isotropic. Okay, so that answers part C. The last thing to check, and the last question that we're asked in part D of this problem, is can the material be further classified as fully isotropic? There's a lot of different ways to look at this as well, but you know, one of the easiest is, all right, if it's fully isotropic, and again, you can consult the notes for this, but if it's fully isotropic, there are a lot of things that have to hold, like you need E1 equal to E2 equal to E3. That's one thing that you can do to check. If you go up to just the original material properties, E1, E2, and E3, you can see straight away that these are not equal. Okay? So E1 is 80 GPa, E2 and E3 are 5.3 GPa. So 80 GPa versus 5.4 roughly GPa. So it's very clear here that the elastic moduli are not the same in all directions, right? Remember what it means to be isotropic. If it's isotropic, it has the same modulus in every direction. So we just checked this and it failed. So that means it is not isotropic. Okay, so that's one way to do it. There are many ways that you can prove that it's not isotropic. That's probably the easiest. Okay, so that's problems number 1, 2, and 3 for the week 3 review packet. I'll stop this video now. Maybe I'll record number 4 and 5, I guess let's say tomorrow. And then we can meet on Wednesday and sort of discuss some of this stuff. All right, see you then.